Welcome to Tech with Kaushik. This is set 9 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam-ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 9. Question number 146. This one focuses on event-driven automation. An architecture relies on an Amazon Event Bridge rule that triggers an AWS Lambda function. The Lambda function processes the event and writes data to an Amazon RDS database. Recently, the RDS database was taken offline for unplanned maintenance for several hours. During this downtime, Event Bridge continued invoking the Lambda function, which failed to write to the database. Because the function exceeded its maximum retry attempts, thousands of events were permanently lost. A DevOps engineer must modify the architecture to ensure events are preserved durably if the database becomes unreachable again. Which solutions will meet this requirement? Choose 2. Identify all valid responses. Options. Option A. Configure an Amazon SQS dead letter queue, DLQ, or an on-failure destination on the Lambda function's asynchronous invocation configuration to capture dropped events. Option B. Introduce an Amazon SQS queue between Event Bridge and the Lambda function by setting the queue as the Event Bridge target and configure the Lambda function to poll the queue synchronously. Option C. Modify the Event Bridge rule to use an Amazon SNS topic as the target and configure a dead letter queue on the SNS topic to catch events that Lambda fails to process. Option D. Enable AWS CloudTrail data events for the Lambda function so that failed executions can be queried and replayed using Amazon Athena. Option E. Replace the RDS database with Amazon DynamoDB, as DynamoDB offers higher availability and built-in event replay buffers. The correct answers are Option A. Configure an Amazon SQS dead letter queue, DLQ, or an on-failure destination on the Lambda function's asynchronous invocation configuration to capture dropped events, and Option B. Introduce an Amazon SQS queue between Event Bridge and the Lambda function by setting the queue as the Event Bridge target and configure the Lambda function to poll the queue synchronously. This works because when Event Bridge targets a Lambda function natively, the invocation is asynchronous. If Lambda fails to process the event, it retries a limited number of times. To prevent loss, you can configure an on-failure destination, or DLQ, directly on the Lambda function, Option A, to store the failed events. Alternatively, you can decouple the architecture completely by routing Event Bridge to an SQS queue and having Lambda poll the queue synchronously, Option B. In this pattern, the event remains durably in the queue until Lambda explicitly deletes it upon successful processing. Let's quickly check the incorrect choices. C. Event Bridge does support DLQs for failed deliveries, but if Event Bridge successfully delivers the event to Lambda and Lambda subsequently fails to process it, the Event Bridge DLQ will not catch it. D. AWS CloudTrail does not log the payload of custom Event Bridge events. It logs API calls. You cannot replay application data payloads from CloudTrail. E. While DynamoDB is highly available, replacing the entire database engine is an extreme architectural change that doesn't inherently solve the event loss problem in the asynchronous messaging layer. Here's a useful exam tip. To prevent data loss during downstream outages in asynchronous Lambda architectures, use Lambda on failure destinations or decouple the compute with an Amazon SQS buffer. Now for question number 147. Consider this situation. A company manages a large multi-account environment using AWS organizations. To adhere to strict security compliance rules, the central security team mandates that the AWS account root user credentials must never be used to perform any actions within any member account. A DevOps engineer has been instructed to enforce this restriction globally across the organization using a service control policy, SCP, attached to the organization root. Which SCP configuration will successfully block the root user from making API calls in member accounts? Here are the options. Option A. Create an SCP with an effective deny, an action of asterisk, and a resource of star. Include a condition block using the string-like operator with the AWS principal ARN, key matching ARN, AWS, IAM, asterisk, root. Option B. Create an SCP with an effective deny, an action of asterisk, and a resource of star. Include a condition block using the string not-like operator with the AWS principal key matching AWS IAM root. Option C. Create an SCP with an effect of allow, an action of and a resource of star. Include a condition block using the string not-like operator with the AWS principal key matching AWS IAM root. Option D. Create an SCP with an effect of deny, an action of and set the principal element explicitly to AWS IAM root. The answer here is option A. Create an SCP with an effect of deny, an action of and a resource of star. Include a condition block using the string-like operator with the AWS principal key matching AWS IAM root. This is the best choice because an SCP with an explicit deny overrides all other permissions. By specifying action, and resource, the SCP blocks all actions. The critical component is the condition block. By checking that AWS principal is string-like AWS IAM root, the deny rule targets only the root user of any member account in the organization, securely locking down root API access without affecting normal IAM users or roles. The remaining options can be eliminated because B. Using string not-like would deny access to everyone except the root user, completely breaking the AWS account by locking out all IAM roles and users. C. SCPs cannot use an allow effect with restrictive conditions to act as a preventative guardrail. Explicit deny is required to override full AWS access and administrator permissions. D. The principal element is not supported in SCPs. SCPs evaluate the principal implicitly based on the account they are attached to. You must use the condition block to target specific identities like the root user. The main takeaway is to restrict root user access using SCPs. You must use a condition block matching AWS principal to AWS IAM root because the principal element cannot be used in SCPs. Question number 148. Let's go. Scenario. An application is deployed globally using a single AWS code pipeline workflow that has sequential stages for us, East 1 and EU West 1. The application uses AWS CloudFormation for deployment. The DevOps team wants to ensure that the deployment in US East 1 is completely healthy and serving traffic properly before the pipeline proceeds to update EU West 1. The health of the application is monitored by an external HTTP health check that drives a CloudWatch alarm. Which approach should the DevOps engineer use to enforce this regional deployment gate with the least custom code? Choices. Option A. Add an invoke action in the pipeline stage immediately after the US East 1 deployment. Target an AWS Lambda function or step functions workflow that checks the status of the CloudWatch alarm and returns a failure status to code pipeline if the alarm is triggered. Option B. Configure a before entry condition on the EU West 1 stage using the AWS code pipeline CloudWatch alarm rule. Reference the US East 1 health alarm and configure the condition to fail or block stage entry when the alarm indicates an unhealthy state. Option C. Install the CloudWatch agent on the underlying infrastructure and configure it to emit a success signal directly to the code pipeline API once the application process starts. Option D. Modify the code pipeline configuration to use AWS Code Deploy instead of CloudFormation, as Code Deploy is the only service that can natively roll back a cross-region pipeline based on an alarm. The right response is option B. Configure a before entry condition on the EU West 1 stage using the AWS code pipeline CloudWatch alarm rule. Reference the US East 1 health alarm and configure the condition to fail or block stage entry when the alarm indicates an unhealthy state. The main reason is code pipeline stage conditions provide a managed CloudWatch alarm rule. A before entry condition on the EU West 1 stage can evaluate the US East 1 health alarm and block the stage when the environment is unhealthy. This implements the deployment gate natively and avoids custom Lambda polling or job result code. A Lambda invoke gate can work, but it requires custom code and is no longer the least custom approach because code pipeline has a native CloudWatch alarm condition rule. C. The CloudWatch agent collects host telemetry. It does not provide a native pipeline stage gate for this CloudFormation deployment. D. Code deploy is not required to gate a CloudFormation pipeline on a CloudWatch alarm, and changing deployment providers would be unnecessary redesign. A helpful shortcut is this. For release gates in current code pipeline, check native stage conditions first. CloudWatch alarm rules can block stage entry based on alarm state without custom Lambda code. Next, question number 149. We're moving on to deployment strategies. Scenario. A development team maintains several microservices using Amazon API Gateway and AWS Lambda. Currently, developers run unit tests locally and manually update the Lambda function code using the AWS CLI. The company wants to modernize this process by enforcing automated unit tests in the cloud. Furthermore, to reduce deployment risk, the new version of a Lambda function must incrementally receive 10% of the traffic every 5 minutes until fully deployed. Which solution will meet these requirements with the least amount of custom scripting? Option A. Create an AWS code pipeline workflow triggered by source code changes. Add an AWS code build stage to execute the unit tests. Add an AWS code deploy stage that uses a custom Lambda deployment configuration with time-based linear percentage set to 10, and linear interval set to 5. Option B. Create an AWS code build project that runs the unit tests and then executes a bash script using the AWS CLI to update the Lambda alias weight. Use a sleep 300 command in a loop to shift traffic incrementally. Option C. Configure an AWS Lambda function to act as a custom Git hook. When code is pushed, the function runs tests, uploads the zip to S3, and updates the Lambda alias routing configuration by 10% recursively using step functions. Option D. Create an AWS code pipeline workflow. Use code build to run tests and package an AWS CloudFormation template. Deploy the template using the CloudFormation pipeline action and rely on CloudFormation's native rolling update policy to shift traffic linearly. In this case, choose option A. Create an AWS code pipeline workflow triggered by source code changes. Add an AWS code build stage to execute the unit tests. Add an AWS code deploy stage that uses a custom Lambda deployment configuration with time-based linear percentage set to 10, and linear interval set to 5. Let's look at the reasoning. Code pipeline can enforce cloud-based unit tests in code build before deployment. Code deploy supports custom Lambda linear traffic shifting configurations, so time-based linear with a 10% increment and a 5-minute interval implements the required progression without a handwritten sleep loop or alias weight orchestration. The other choices do not work because B. A code build sleep loop and manual alias updates add custom scripting and fragile state management that code deploy can handle. C. A custom Git hook plus step functions duplicates native pipeline, test, and deployment capabilities and creates substantially more custom logic. D. CloudFormation alone does not provide the required incremental Lambda alias traffic shifting. Code deploy integration is needed for managed gradual deployment. Code deploy has predefined Lambda canary/linear configurations, but not every interval is predefined. Use a custom time-based linear configuration when the required increment interval is not built in. Question number 150. A DevOps engineer is using AWS code deploy to perform an in-place deployment to an Amazon EC2 auto-scaling group containing 5 instances. The deployment is configured with the code deploy default, one at a time rule. During the deployment process, a sudden spike in traffic causes the auto-scaling group to scale out by launching 2 additional instances. When the code deploy console reports the deployment as successful, the engineer connects to the fleet and realizes that the 2 newly launched instances are running the old version of the application, while the original 5 instances are running the new version. What is the underlying cause of this discrepancy? Choice A. Auto-scaling launched the new instances while the code deploy deployment was still in progress. Code deploy applies the last known completely successful revision to new instances, which was the older version. Choice B. The AWS code deploy agent on the newly launched instances failed to authenticate with the code deploy service, causing the deployment lifecycle hooks to be skipped. Choice C. The one-at-a-time deployment configuration explicitly prevents code deploy from updating newly launched auto-scaling instances to prevent race conditions during a scale-out event. Choice D. The application load balancer, ALB, health checks failed on the new instances, causing code deploy to automatically roll back those specific instances to the previous application revision. The best choice is option A. Auto-scaling launched the new instances while the code deploy deployment was still in progress. Code deploy applies the last known completely successful revision to new instances, which was the older version. Here's why. AWS Code Deploy integrates closely with EC2 auto-scaling. If an auto-scaling scale-out event occurs while a code deploy deployment is currently in progress, Code Deploy automatically deploys the last known successful application revision to the newly launched instances. Because the current deployment has not yet reached a globally successful state across the fleet, the last known successful revision is the older version of the application. Here's why the alternatives are not suitable. B. If the code deploy agent failed to authenticate, the instances would fail their deployment lifecycle hooks entirely and would likely be terminated by auto-scaling health checks, rather than successfully serving the old version. C. The one-at-a-time configuration dictates how many instances are taken offline simultaneously during the deployment. It does not explicitly block scale-out updates. D. If the ALB health check fails during deployment, Code Deploy halts the deployment. It does not selectively roll back only the new instances while leaving the original 5 running the new version. Exam tip. Instances launched by an auto-scaling group during an active code deploy deployment will receive the application revision from the most recent, fully completed successful deployment, the older version. Here comes question number 151. Here's what is happening. A DevOps team wants to ensure that engineering users cannot directly attach an elastic IP address to Amazon EC2 instances running in a production environment. The team must enforce a deny policy preventing the attachment action and must be automatically alerted if any production instance is found to have an elastic IP address attached. Which solution will automate these tasks with the least operational overhead? Review the options. Choice A. Deploy an AWS CloudFormation stack set to configure an AWS Lambda function that queries AWS CloudTrail every minute for associate address events, detaches the IP, and sends an Amazon SNS alert. Choice B. Attach an IAM policy to the engineering team's IAM roles denying the EC2 associate address action. Deploy an AWS config rule to monitor instances tagged as production and alert the security team if an elastic IP is attached. Choice C. Remove the EC2 associate address permission from all IAM boundaries. Create an Amazon Event Bridge scheduled rule to invoke an AWS Lambda function hourly that lists all elastic IPs and notifies the security team. Choice D. Create an AWS config conformance pack that checks if EC2 instance profiles contain the deny EC2 associate address permission. Create a second rule to verify elastic IP attachments and alert via Amazon SNS. Go with option B. Attach an IAM policy to the engineering team's IAM roles denying the EC2 associate address action. Deploy an AWS config rule to monitor instances tagged as production and alert the security team if an elastic IP is attached. This approach combines preventative and detective controls efficiently. Denying the action via IAM prevents unauthorized attachments proactively. Using AWS config provides continuous detective compliance to alert the security team if an elastic IP is attached through other means, for example, a misconfigured automation role, requiring the least operational overhead compared to custom polling scripts. Now let's rule out the other options. A. Querying CloudTrail every minute using Lambda is inefficient, expensive, and heavily custom compared to native AWS config rules. C. A scheduled Lambda function running hourly creates a delay in detection and adds custom code maintenance overhead. Removing permissions from boundaries is less direct than an explicit deny policy. D. AWS config cannot easily evaluate the contents of attached instance profiles for specific IAM permissions in this manner. IAM access analyzer or custom scripts would be needed, adding complexity. Keep this point in mind for the exam. When asked for the least overhead for configuration compliance, favor AWS config managed rules over custom Lambda polling of CloudTrail or custom scripts. Question number 152. A large enterprise uses AWS organizations to manage separate AWS accounts for its business units. A central infrastructure team needs to automate a monthly refresh of a standard Amazon Linux 2023 Golden AMI, so it includes current operating system updates and a required security monitoring agent. The newly generated AMI must then be made available to all business unit accounts. Which solution meets these requirements with the least management overhead? Choices. Option A. Launch an Amazon EC2 instance from the current base AMI by using an AWS Lambda function. Run custom scripts to update the operating system and install the security agent. Create a new AMI and modify its launch permissions with additional Lambda code. Option B. Use AWS Systems Manager automation to update a running EC2 instance and create an AMI. Store the new AMI ID in AWS Systems Manager parameter store and build custom cross-account replication logic for each business unit. Option C. Create a scheduled EC2 image builder image pipeline that uses the current Amazon Linux 2023 parent image and a build component to install the security agent. Configure an image builder distribution configuration to grant the organization or target OUS launch permissions for the output AMI or to distribute AMI copies to the target accounts. Option D. Use AWS Resource Access Manager, AWS RAM, to share the image builder image recipe and components with every business unit account and require each business unit to run its own image pipeline. The best choice is option C. Create a scheduled EC2 image builder image pipeline that uses the current Amazon Linux 2023 parent image and a build component to install the security agent. Configure an image builder distribution configuration to grant the organization or target OUS launch permissions for the output AMI or to distribute AMI copies to the target accounts. This works because EC2 Image Builder is purpose-built to automate recurring image builds, testing, customization, and distribution. An image builder distribution configuration can authorize AWS accounts, AWS organizations, or organizational units to launch the output AMI, and it can also distribute AMI copies to specified target accounts. This directly satisfies centralized golden image creation and cross-account distribution without custom polling or replication code. Let's quickly check the incorrect choices. A. Custom Lambda-driven instance launches, patch scripts, image creation, and permission changes recreate functionality that Image Builder already manages. B. Systems Manager automation can participate in image maintenance workflows, but custom parameter store replication does not distribute or authorize use of the AMI and adds unnecessary cross-account logic. D. AWS RAM can share supported Image Builder resources such as components, recipes, and Image Builder image resources, but output AMIs are distributed through Image Builder distribution settings and EC2 AMI launch permissions. Requiring every business unit to build its own image also defeats centralized golden image management. Here's a useful exam tip. For recurring golden AMI creation, use EC2 Image Builder. For the resulting AMI, use Image Builder distribution settings and EC2 launch permissions for accounts, organizations, or OUs. Do not confuse this with sharing Image Builder design resources through AWS RAM. Next, question number 153. Next, let's move into code deploy and auto-scaling. Scenario. A company runs a critical memory-intensive application on Amazon EC2 instances within an auto-scaling group. The DevOps team must implement an in-place deployment strategy that updates one instance at a time so the remaining fleet can handle traffic. The deployment must automatically roll back if the average memory utilization metric of the ASG exceeds 80% during the deployment process. Which combination of services and configurations will meet these requirements? Options. Option A. Use AWS Elastic Beanstalk with an auto-scaling group. Configure a rolling deployment with a batch size of 1. Enable enhanced health reporting to monitor the instances and automatically roll back using Elastic Beanstalk triggers. Option B. Use AWS Systems Manager automation to perform a blue/green deployment on the auto-scaling group. Set a CloudWatch alarm for memory utilization and configure the automation runbook to halt and revert changes if the alarm breaches. Option C. Use AWS Code Deploy with the auto-scaling group. Configure a deployment group with the code deploy default .1 at a time deployment configuration. Set up a CloudWatch alarm for memory utilization and configure automatic rollbacks in code deploy on alarm threshold breaches. Option D. Use AWS CloudFormation to update the auto-scaling group. Use an auto-scaling lifecycle hook to pause instances. Use an AWS step function state machine to deploy the code, monitor memory utilization, and issue a rollback signal if it exceeds 80%. The answer here is option C. Use AWS Code Deploy with the auto-scaling group. Configure a deployment group with the code deploy default .1@a-time deployment configuration. Set up a CloudWatch alarm for memory utilization and configure automatic rollbacks in code deploy on alarm threshold breaches. This is the best choice because AWS Code Deploy integrates natively with Amazon EC2 auto-scaling groups. The code deploy default .1@a-time configuration natively handles updating one instance at a time to maintain capacity. Code deploy natively supports automated rollbacks triggered by CloudWatch alarms, such as high memory utilization, rolling back the deployment safely without requiring custom orchestration. The remaining options can be eliminated because Elastic Beanstalk rolling deployments do not natively integrate direct automatic rollbacks triggered by arbitrary CloudWatch alarms in the way Code Deploy does without extensive custom EB extensions. B. Systems Manager Automation does not provide native blue/green traffic shifting and health tracking for ASGs as easily as Code Deploy. D. Using step functions and lifecycle hooks requires significant custom development and management overhead to reinvent what Code Deploy handles natively. The main takeaway is when deploying to an ASG with requirements for complex deployment speeds, for example, one at a time, half at a time, and automated alarm-based rollbacks, AWS Code Deploy is the native, lowest overhead choice. Question number 154. Let's go. A development team currently stores source code for various projects in shared network drives, leading to code conflicts and lost work as the team grows. The team wants to adopt a version control system and establish automated deployment pipelines. Code pushed to a testing branch must automatically deploy to a test environment, while code merged into the production branch must automatically deploy to the production environment. What is the most operationally efficient way to meet these requirements? Option A. Create an AWS code commit repository for each project. Use a test branch for the test environment and a main branch for production. Create separate deployment pipelines triggered by their respective branches, using pull requests to merge code from test to main. Option B. Migrate the code to version-enabled Amazon S3 buckets. Use AWS Code Pipeline to monitor S3 bucket changes. Create an AWS Lambda function to move approved code from the testing bucket to the production bucket. Option C. Create an AWS code commit repository for each project. Use a single main branch for both environments. Create an AWS code pipeline that deploys to the test environment, waits for a time delay, and then deploys to the production environment. Option D. Enable versioning and branching on Amazon S3 buckets for each project. Map the test environment to the S3 testing prefix and the production environment to the S3 main prefix. Use S3 event notifications to trigger AWS code deploy directly. The right response is option A. Create an AWS code commit repository for each project. Use a test branch for the test environment and a main branch for production. Create separate deployment pipelines triggered by their respective branches, using pull requests to merge code from test to main. The main reason is this is the standard Git flow-based CI/CD architectural pattern. Code commit provides managed version control to prevent conflicts. Branch-based pipeline triggers in AWS Code Pipeline allow developers to push to a test branch to deploy to the test environment automatically. A pull request is used to review the code before merging to main, which subsequently triggers the production pipeline. B. Using S3 as a primary version control system, VCS, does not handle merges, conflict resolution, or standard Git workflows, making it unsuitable for a growing developer team. C. Using a single branch and placing a time delay before deploying to production is unsafe and does not match the requirement of deploying when code is pushed to specific respective branches. D. Branching is a Git concept, not an S3 concept. S3 versioning does not support branches or pull requests. A helpful shortcut is this. Associate source code management and collaborative branching/merging requirements with Git-based services like AWS Code Commit rather than Amazon S3. Next up is question number 155. The focus now shifts to ASG health and monitoring. Here's the scenario. A DevOps engineer discovers that an application running on Amazon EC2 instances in an auto-scaling group behind an application load balancer, ALB, has stopped responding to users. The instances are failing ALB health checks. System logs indicate a gradual memory exhaustion leading to the application crashing, though the EC2 status checks remain healthy. Which combination of actions will improve the resilience of the application and provide automated alerting for this issue? Choose 2. Choose every option that satisfies the requirement. The choices are: Option A, modify the target group health check configuration from HTTP to TCP to ensure port availability is monitored. Option B, update the auto-scaling group configuration to use elastic load balancing, ELB. Health check so instances are replaced when the application crashes. Option C, decrease the target group health check interval seconds parameter to fail health checks faster. Option D, install the Amazon CloudWatch agent on the EC2 instances to collect memory metrics. Create a CloudWatch alarm on high memory utilization to trigger an Amazon SNS notification. Option E, enable the standard Amazon CloudWatch memory consumption metric for the auto-scaling group and create an alarm attached to an Amazon SNS topic. You should choose Option B. Update the auto-scaling group configuration to use elastic load balancing, ELB. Health checks so instances are replaced when the application crashes, and Option D. Install the Amazon CloudWatch agent on the EC2 instances to collect memory metrics. Create a CloudWatch alarm on high memory utilization to trigger an Amazon SNS notification. Let's look at the reasoning. If an application crashes but the OS remains running, EC2 status checks will report healthy, but the ALB HTTP health check will fail. Updating the ASG to use ELB health checks. B. Ensures the ASG replaces the unresponsive instance. Because memory utilization is an OS-level metric, it requires the CloudWatch agent, D, to be installed to collect it and trigger alarms. The other choices do not work because A. TCP health checks only verify if the port is listening, not if the application is functioning correctly. HTTP checks are superior for application health. C. Decreasing the health check interval detects the failure faster but does not replace the instance if ASG isn't using ELB checks or monitor the memory exhaustion. E. EC2 does not provide memory metrics by default. The standard metric set only includes CPU, disk, and network. Memory requires an agent. Memory and disk space are guest OS metrics. They always require the CloudWatch agent. To replace instances failing application-level checks, enable ELB health checks on the ASG. Here comes question number 156. Here's the scenario. A financial services firm runs a large fleet of Amazon EC2 instances with EBS-backed root volumes. Occasionally, AWS schedules underlying hardware maintenance, resulting in EC2 instance retirement events. A DevOps engineer needs to automate the restart of affected instances to move them to healthy hardware as soon as the retirement event is scheduled, minimizing manual intervention. How should the DevOps engineer automate this task? The choices are: Choice A, enable EC2 auto recovery for all instances. Deploy an AWS config rule to restrict recovery actions to non-business hours. Choice B, create an Amazon Event Bridge rule that captures AWS health events for EC2 instance retirement. Set the target to an AWS Systems Manager automation runbook that stops and starts the affected instance. Choice C, create an Amazon Event Bridge scheduled rule that runs weekly to trigger an AWS Lambda function. The function will poll for scheduled retirements and restart the instances. Choice D, set up an Amazon CloudWatch alarm on the status check failed_system metric. Configure the alarm action to reboot the instance when the metric exceeds the threshold. In this case, choose Option B. Create an Amazon Event Bridge rule that captures AWS health events for EC2 instance retirement. Set the target to an AWS Systems Manager automation runbook that stops and starts the affected instance. Here's why. AWS Health publishes events to Amazon Event Bridge when an EC2 instance is scheduled for retirement. For example, AWS_EC2_instance_retirement_scheduled. By capturing this event, Event Bridge can automatically trigger an SSM automation runbook, AWS, restart EC2 instance, or custom stop/start to migrate the instance to new underlying hardware proactively. Here's why the alternatives are not suitable. A. EC2 auto recovery is used for unexpected hardware failures, status check failed_system, not scheduled maintenance retirements. C. A scheduled Lambda polling script introduces delays and unnecessary custom code overhead compared to a native event-driven architecture. D. A scheduled retirement does not immediately cause a status check failed _ system error. The instance is simply scheduled to be retired in the future. Exam tip. For scheduled events, use AWS Health integrated with Amazon Event Bridge for event-driven automation instead of polling APIs. Now for question number 157. This question takes us into EKS auto-scaling. Consider this situation. A company deployed a new web application to an Amazon Elastic Kubernetes service, EKS, cluster. The cluster uses an application load balancer to route traffic. Immediately after deployment, each application pod has a short, CPU-intensive initialization phase. The pods are being reported as ready while that initialization work is still occurring. So the horizontal pod autoscaler, HPA, interprets the startup CPU usage as normal workload demand and rapidly scales to the maximum number of replicas before user traffic arrives. Which solution will most effectively prevent the initialization CPU spike from driving unnecessary HPA scale-out? Review the options. Option A. Implement the vertical pod autoscaler, VPA, so that pod CPU requests are increased during initialization. Option B. Configure a startup probe or a readiness probe with an appropriate initial delay so that pods do not become ready until the CPU-intensive initialization phase has completed. Option C. Replace the horizontal pod autoscaler with the Kubernetes cluster autoscaler so that pod replica counts are based on node capacity instead of CPU utilization. Option D. Increase the HPA scale-up stabilization window seconds value so that startup CPU samples are ignored until the stabilization window expires. Go with option B. Configure a startup probe or a readiness probe with an appropriate initial delay so that pods do not become ready until the CPU-intensive initialization phase has completed. For CPU-based HPA decisions, Kubernetes treats not yet ready pods specially during startup. Kubernetes guidance recommends using a startup probe that does not pass until the CPU spike is finished or delaying readiness until initialization completes. This prevents initialization-only CPU consumption from being treated as representative workload demand and is the most direct fix for the stated behavior. Now let's rule out the other options. A. VPA adjusts pod resource requests or limits. It does not solve the problem of HPA, interpreting initialization CPU as workload demand. C. The cluster autoscaler changes node capacity when pods cannot be scheduled. It does not replace HPA replica management for application load. D. HPA stabilization windows are primarily intended to reduce replica count flapping by considering recent scale recommendations. They do not make startup CPU samples inherently invalid, and Kubernetes specifically recommends readiness/startup handling for initialization CPU spikes. Keep this point in mind for the exam. When CPU-based HPA reacts to application warm-up, make initialization visible through startup or readiness probes so HPA can exclude not yet ready pods appropriately. Next up is question number 158. An organization enabled Amazon may see automated sensitive data discovery across numerous Amazon S3 buckets. Several buckets store only AWS CloudTrail logs, and a known set of lower environment buckets contains synthetic test data with no real user information. A DevOps engineer must reduce automated discovery cost while preserving discovery coverage for production data. Which solutions will meet these requirements? Choose two. More than one answer may be correct. Here are the options. Option A. Add the S3 buckets that store only CloudTrail logs to the Macy Automated Discovery exclusion list. Option B. Exclude buckets from automated discovery based only on the last modified date of their objects. Option C. Configure Macy to exclude every S3 object whose key contains the word test without changing the bucket classification scope. Option D. Add the known lower environment test buckets to the Macy Automated Discovery exclusion list. Option E. Disable automated sensitive data discovery entirely and rely only on occasional manual review of production buckets. The answers that work here are Option A. Add the S3 buckets that store only CloudTrail logs to the Macy Automated Discovery exclusion list, and Option D. Add the known lower environment test buckets to the Macy Automated Discovery exclusion list. This works because Macy Automated Sensitive Data Discovery lets an administrator exclude specific S3 buckets from the classification scope. Excluding known buckets that contain only Cloud Trail logs or synthetic lower environment data reduces unnecessary discovery activity while retaining automated discovery for production buckets. Let's quickly check the incorrect choices. B. Automated discovery exclusion scope is configured for specific buckets. It is not defined dynamically from object last modified dates. C. Automated discovery exclusions are not arbitrary object key filtering rules. The supported scope control for this requirement is to exclude the known buckets. E. Disabling automated discovery removes the continuous production data visibility that the scenario explicitly requires. Here's a useful exam tip. For MECI automated sensitive data discovery, optimize scope by excluding specific known S3 buckets that do not need classification while keeping production buckets in scope. Question number 159. This is a hard-level item, so avoid choosing too quickly. Here's what is happening. A company hosts a REST API using Amazon API Gateway with a regional custom domain name. To comply with strict security requirements for B2B partner integrations, the custom domain must require mutual TLS, MTLS, authentication. The partners already have client certificates issued by trusted certificate authorities. Which combination of steps must a DevOps engineer take to configure MTLS for the custom domain? Choose 2. Select all answers that apply. Choice A. Reissue every partner client certificate from AWS Certificate Manager Private Certificate Authority, ACM-PCA. Choice B. Create a PM trust store containing the root and intermediate CA certificates that are trusted to issue partner client certificates, and upload the trust store to an Amazon S3 bucket. Choice C. Upload the partner client certificate private keys to an Amazon S3 bucket so API Gateway can validate signatures. Choice D. Import every individual partner client certificate into AWS Certificate Manager and configure those ACM certificates as the API Gateway Trust Store. Choice E. Configure the API Gateway custom domain name with the Amazon S3 Trust Store URI for MTLS. The required selections are Option B. Create a PM trust store containing the root and intermediate CA certificates that are trusted to issue partner client certificates, and upload the trust store to an Amazon S3 bucket, and Option E. Configure the API Gateway custom domain name with the Amazon S3 Trust Store URI for MTLS. This is the best choice because API Gateway Mutual TLS for a custom domain uses a trust store stored in Amazon S3. The trust store contains the trusted root and intermediate CA certificates used to validate client certificate chains. The custom domain configuration then references the S3 Trust Store URI. The client certificates can be issued by a supported public or private CA. They do not have to be issued by ACM-PCA. The remaining options can be eliminated because A. ACM-PCA is one possible issuer for client certificates, but API Gateway MTLS does not require partner certificates to be issued by ACM-PCA. C. Client private keys must remain with the clients and must never be uploaded to the API Gateway Trust Store. D. API Gateway MTLS uses an S3 Trust Store of trusted CA certificates, not individual ACM client certificate imports, as the Trust Store. The main takeaway is for API Gateway MTLS. Remember, regional custom domain, server certificate for the domain, and an S3 Trust Store containing the trusted client certificate CA chain. Now for question number 160. Here's the scenario. An AWS Lambda function is configured to trigger when new objects are uploaded to an Amazon S3 bucket. The function reads the object and writes parse data to an Amazon DynamoDB table. The function's execution role has the necessary S3, getObject, and DynamoDB, put item permissions. However, the Lambda function is not invoking when files are uploaded to the bucket. Which configuration change will resolve this issue? The choices are: Choice A. Attach a resource-based policy to the Lambda function that grants the S3.AmazonAWS.com service principal permission to invoke the function. Choice B. Update the S3 bucket policy to grant the Lambda execution role permission to perform the Lambda invoke function action. Choice C. Add the Lambda invoke function permission to the existing Lambda execution role. Choice D. Configure an Amazon Simple Queue Service, SQS, queue between the S3 bucket and the Lambda function to manage the event payload delivery. In this case, choose option A. Attach a resource-based policy to the Lambda function that grants the S3 to AmazonAWS.com service principal permission to invoke the function. The main reason is for an Amazon S3 bucket to trigger an AWS Lambda function asynchronously. S3 must be explicitly granted the Lambda invoke function permission. This is achieved by adding a resource-based policy to the Lambda function itself, allowing the S3 service principal, S3 to AmazonAWS.com, to invoke it. B. S3 buckets do not use execution roles to call other services. They rely on resource-based policies attached to the target resource, the Lambda function. C. The Lambda execution role determines what Lambda can do after it runs, like writing to DynamoDB. It does not control what external services can invoke the function. D. Provisioning SQS does not resolve the root IAM permission issue between S3 and Lambda. A helpful shortcut is this. Remember the distinction between execution roles, what the function can access, and resource-based policies, who can invoke the function. S3 events require a resource-based policy on the Lambda function. Next up is question number 161. We're moving on to EC2 tenancy compliance. Here's what is happening. A healthcare organization must strictly license third-party software based on underlying hardware. A DevOps engineer needs an automated auditing solution to verify that all Amazon EC2 instances running this software use dedicated host tenancy. The solution must identify non-compliant instances with the least administrative overhead. How should the DevOps engineer implement this requirement? Here are the options. Option A. Enable AWS CloudTrail to monitor the Run Instances API. Configure an Amazon Event Bridge rule to trigger an AWS Lambda function that stores non-compliant instance IDs in an Amazon RDS database. Option B. Use AWS Systems Manager State Manager to run a daily script on all instances to query their placement tenancy and write the results to an Amazon DynamoDB table. Option C. Enable AWS config recording for EC2 instances and deploy the desired instance tenancy managed rule with the tenancy parameter set to host. Option D. Launch a central EC2 worker instance running a script that continuously polls the EC2 API for instance placement attributes and sends alerts for instances that are not on dedicated hosts. The best choice is option C. Enable AWS config recording for EC2 instances and deploy the desired instance tenancy managed rule with the tenancy parameter set to host. Let's look at the reasoning. AWS config provides the desired instance tenancy managed rule for evaluating the tenancy of EC2 instances. Setting tenancy to host evaluates whether the recorded EC2 instances use dedicated host tenancy. Because the required evaluation already exists as a managed rule, this provides continuous compliance auditing without custom Lambda evaluation code. The other choices do not work because A. CloudTrail captures API activity, but a custom event bridge and Lambda workflow adds code and does not provide the same native configuration compliance history. B. A daily in-instance script is slower, requires managed node coverage, and adds custom data storage and script maintenance. D. A continuously running polling instance adds infrastructure, code, cost, and operational overhead that AWS config avoids. Before writing a custom AWS config rule, check the managed rule catalog. Use desired instance tenancy with host when compliance depends on EC2 dedicated host tenancy. Here comes question number 162. A DevOps team is deploying a Node.js web application to a production environment. The application requires a PostgreSQL database. The data is highly critical and must survive independent of the application compute layer's lifecycle. The deployment process must automatically roll back in case of health check failures and must notify the team via email if a failure occurs. Which combination of steps will meet these requirements? Choose 3. Identify all valid responses. Choice A. Use the rolling deployment method in AWS Elastic Beanstalk to update the application versions in place. Choice B. Provision the Amazon RDS for PostgreSQL instance externally, decoupled from the AWS Elastic Beanstalk environment lifecycle. Choice C. Configure the AWS Elastic Beanstalk environment notifications setting with an email address to alert the team on deployment failures. Choice D. Provision the Amazon RDS for PostgreSQL database instance directly within the AWS Elastic Beanstalk environment configuration. Choice E. Use the immutable deployment method in AWS Elastic Beanstalk to launch new instances and automatically roll back if they fail health checks. Choice F. Create an Amazon Event Bridge rule tracking AWS CloudTrail API calls for the deployment, targeting an Amazon SNS topic for failure alerts. The required selections are Option B. Provision the Amazon RDS for PostgreSQL instance externally, decoupled from the AWS Elastic Beanstalk environment lifecycle. Option C. Configure the AWS Elastic Beanstalk environment notifications setting with an email address to alert the team on deployment failures. And Option E. Use the immutable deployment method in AWS Elastic Beanstalk to launch new instances and automatically roll back if they fail health checks. Here's why. To ensure the database survives the application stack state, for example, if the EB environment is terminated, the RDS instance must be provisioned outside the EB environment. B. Elastic Beanstalk supports native email notifications for environment events, including failures. C. Immutable deployments launch a full replacement set of instances in a separate auto-scaling group. If the new instances fail health checks, Elastic Beanstalk terminates them and leaves the original instances serving traffic. E. Here's why the alternatives are not suitable. A. Rolling deployments update instances in place, which can cause capacity reduction and complex rollbacks compared to immutable deployments. D. A coupled RDS database can be configured with a retained deletion policy, but Option D does not establish the required independent database lifecycle. Provisioning the database externally is the clearer production design for lifecycle independence. F. Using EventBridge and CloudTrail to track deployment AP is as much more complex than using EB's native environment notifications. Exam tip. For production Elastic Beanstalk workloads that require database lifecycle independence, provision RDS externally from the Elastic Beanstalk environment. Immutable deployments provide the safest automated rollback behavior. Question number 163. Consider this situation. A compliance mandate requires a QA lead to explicitly sign off on all application releases before AWS Code Pipeline deploys them to the production environment. The organization must securely record and retain the identity of the person who provided the approval. Which combination of actions will satisfy these requirements? Choose 2. More than one answer may be correct. Review the options. Option A. Create an AWS Lambda function triggered by the pipeline to pause the deployment until an external API call confirms approval. Option B. Add a manual approval action to the pipeline before the production deployment stage and restrict approval permissions using IAM policies. Option C. Configure AWS Code Pipeline to output a deployment manifest to Amazon S3 containing the approver's credentials. Option D. Enable an AWS CloudTrail trail to log API events and deliver them to an Amazon S3 bucket for retention. Option E. Enable AWS Code Pipeline execution history logging directly to Amazon CloudWatch logs for audit retention. The answers that work here are Option B. Add a manual approval action to the pipeline before the production deployment stage and restrict approval permissions using IAM policies. And Option D. Enable an AWS CloudTrail trail to log API events and deliver them to an Amazon S3 bucket for retention. AWS Code Pipeline natively supports manual approval actions, which halt pipeline execution until a designated user approves it. IAM policies control exactly who is authorized to invoke the put approval result API. AWS CloudTrail automatically records this API call, capturing the IAM identity of the approver and delivers it to S3 for secure, long-term compliance retention. Now let's rule out the other options. A. Using a custom Lambda function to pause for a third-party API is unnecessary when Code Pipeline has native manual approval actions. C. Code Pipeline does not natively output a deployment manifest detailing who approved a manual step to S3. E. Code Pipeline execution history displays approval metadata in the console, but it is not natively pushed to CloudWatch logs as structured audit records in the same immutable way CloudTrail provides. Keep this point in mind for the exam. For compliance auditing of who did what in AWS, including pipeline approvals, AWS CloudTrail is the primary source of truth. Next up is question number 164. Consider this situation. A development team is building a serverless application using AWS SAM. The team uses AWS Code Commit for version control. They require two automated CI/CD pipelines, one for a testing environment and one for a production environment. The testing environment should deploy automatically when code is pushed to the test branch. The production environment must require a manual approval step before deployment when code is pushed to the main branch. How should a DevOps engineer architect this workflow? Here are the options. Option A. Create a single AWS code commit repository with a test branch and a main branch. Create two separate AWS code pipelines, each triggered by its respective branch. Add a manual approval action to the production pipeline. Option B. Create two separate AWS code commit repositories. Configure a single AWS code pipeline that pulls both repositories. Add a conditional manual approval action based on the repository source. Option C. Create a single AWS code commit repository with a single main branch. Create one AWS code pipeline that deploys to testing automatically, then pauses at a manual approval stage before deploying to production. Option D. Create an AWS code build project that builds the SAM application and pushes it to Amazon S3. Trigger AWS CloudFormation to deploy to testing or production based on object tags, using SNS for manual approval. The answer here is Option A. Create a single AWS code commit repository with a test branch and a main branch. Create two separate AWS code pipelines, each triggered by its respective branch. Add a manual approval action to the production pipeline. This works because this is the standard and most efficient implementation for branch-based CI/CD in AWS. You use one code commit repository containing multiple branches, test, and main. You construct two separate code pipeline instances, each configured to pull a different branch. The test pipeline deploys automatically, while the main pipeline includes a manual approval action before its AWS CloudFormation deployment stage. Let's quickly check the incorrect choices. B. Using two entirely separate repositories for different deployment environments creates severe code synchronization overhead and anti-patterns for Git version control. C. Code pipelines are triggered by a single branch configuration per source action. A single pipeline cannot listen to multiple branches simultaneously and branch its logic dynamically based on the source branch. D. Code build is for building, not for complete pipeline orchestration or manual approvals. Code pipeline is required to orchestrate the stages and approvals. Here's a useful exam tip. AWS code pipeline source actions bind to a specific branch. If you need distinct behavior based on different branches, like test versus prod, deploy separate pipelines for each branch. Here comes question number 165. This question takes us into service quota automation. Multiple engineering teams share a single AWS account. The platform manager needs an automated alert through a third-party HTTPS webhook whenever usage of a service quota supported by AWS Service Quotas automatic management approaches its allocated limit. The solution should minimize custom code and ongoing quota-by-quota configuration. Which solution will accomplish this with the least custom development and operational overhead? Review the options. Choice A. Deploy an AWS Lambda function that enumerates resources for every AWS service, compares the counts with hard-coded limits, and runs hourly from an Amazon EventBridge schedule. Choice B. Start AWS Service Quotas automatic management in notify-only mode. Create an Amazon EventBridge rule for service quotas utilization events and route matching events to an EventBridge API destination configured for the third-party webhook. Choice C. Create a separate Amazon CloudWatch alarm manually for every service quota that exposes an AWS/usage metric. Publish each alarm to Amazon SNS and invoke a Lambda function that calls the webhook. Choice D. Enable AWS config and create custom rules that count resources against service quotas. Then invoke a systems manager automation runbook to call the webhook. The right response is option B. Start AWS Service Quotas automatic management in notify-only mode. Create an Amazon EventBridge rule for service quotas utilization events and route matching events to an EventBridge API destination configured for the third-party webhook. This is the best choice because service quotas automatic management monitors supported quota utilization and emits notifications when usage approaches defined thresholds. Service quotas integrates with EventBridge for event-driven automation. Routing those events to an Event Bridge API destination lets the account call a third-party HTTPS endpoint without maintaining quota polling code or a Lambda webhook forwarder. The remaining options can be eliminated because A. Resource enumeration and hard-coded quotas require extensive custom logic and become stale as services and quotas change. C. CloudWatch quota alarms remain useful, but manually configuring an alarm for each quota creates more ongoing work and does not take advantage of automatic management's centralized quota monitoring. D. AWS config is designed for configuration compliance, not as a general-purpose service quota utilization engine. Custom counting rules would add substantial development overhead. The main takeaway is for current quota monitoring. Check AWS service quotas automatic management before building per quota polling. Event Bridge can route service quotas events directly into automation or external API destinations. Now for question number 166. Here's the scenario. A DevOps engineer uses AWS CloudFormation to provision an Amazon ECS cluster and an Amazon EC2 auto-scaling group to launch EC2 container instances. After the CloudFormation stack creation successfully completes, the engineer notices that the newly launched EC2 instances are registering to the default ECS cluster instead of the newly created custom ECS cluster. How should the engineer modify the CloudFormation template to fix this issue? The choices are: Choice A. Add the ECS cluster name to the custom resource logic in the CloudFormation template to manually move instances post-launch. Choice B. Include the ECS cluster reference inside the AWS ECS service resource definition so the service automatically binds the instances. Choice C. Update the user data property of the AWS EC2 launch template resource used by the auto-scaling group to append ECS_cluster equals custom cluster name to /etc/ECS/ECS.config using a CloudFormation reference or substitution for the created ECS cluster name. Choice D. Add an explicitly defined depends on attribute to the auto-scaling group resource pointing to the ECS cluster resource to enforce registration order. Go with option C. Update the user data property of the AWS EC2 launch template resource used by the auto-scaling group to append ECS_cluster equals custom cluster name to /etc/ECS/ECS.config using a CloudFormation reference or substitution for the created ECS cluster name. The main reason is when using the EC2 launch type for Amazon ECS, the ECS container agent running on the EC2 instances registers with the cluster named default by default. To register the instances to a custom ECS cluster, the cluster name must be explicitly passed to the agent by modifying the /etc/ECS/ECS.config file within the EC2 user data of the launch template. A. Custom resources are not required for this. Bootstrapping via user data is the native way to configure the ECS agent. B. The AWS ECS service resource determines where tasks run, but it does not control which cluster the underlying EC2 instances join. D. The depends on attribute manages creation order, but does not inject the cluster name into the EC2 instance OS. The instance will still join the default cluster. A helpful shortcut is this. If an EC2 instance launched for ECS fails to join the intended cluster, check the user data script to ensure ECS_cluster is defined in /etc/ECS/ECS.config. You have completed set 9 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.